Thank you very much for coming to my talk. My name is Samin Ishtiaq. I'm at Ribble, and I'll be talking about the fault-tolerant extension for your quantum control system. So this is a control system session. My assumption here is that a lot of you are super users of control systems, right? Even developers of control systems. And actually, can I just have a vote, like who's developing control systems here? That's great, because all of you, thank you for coming to my talk, but you guys are really special here. Okay, so what I want to talk to you about is what is the first fault-tolerant program you want to run on your control system? Okay, so what that program is. And then I want to talk about how you want to take your control system and what features you want to add to it to make it possible for you to run that first fault-tolerant program, okay? So I'd say hello world here. So if you programmed before, you know hello world is the first program you write. So this is the first program you want to write to run on your control system, the first fault-tolerant one. Okay, so I'll tell you straight away, the first fault-tolerant program you want to write and run is a quantum memory, right? So you've seen this before, you've been here 3 days now. You'll have seen on the left-hand side is a 3x3 surface code patch. So it represents, in superconducting systems, other systems are available. In superconducting systems, this represents a logical qubit, right? And what a quantum memory program is about is keeping this logical qubit alive for so many rounds, right? Now, on the right-hand side, I'm going to zoom into this code a bit, so you don't have to look at this code right now. On the right-hand side is the code that implements quantum memory. The code is written in OpenQASM 3, and I don't want you to hurt your eyes, so let's just zoom into a couple of points here. So this code should be runnable by your control system mostly right now, right? So what your code does is it's going to run certain gates. These gates will extract the syndromes from your logical qubit. At the end of this, you want to do a measurement of the auxiliaries, right? Now, why are you doing this? You're doing this because you want to check that the logical patch is in the state you expect it to be, right? And the control system's job is to run these gates, right? So what you want to do with the measurements is send them to the quantum error correction system, right? It could be on your system, it could be somewhere else, but you want to send it somewhere else. It's a different functional block. You want to send it somewhere else. You want to wait for it to do decoding. So that's the action 2 shown here. And then when the decoding is done, you want to receive the observable back from the quantum error correction system, okay? So this is what will happen on the control system. Kind of correspondingly, right? The corresponding actions on the QECi system are these. It will wait there, it will receive the measurements from the control system, it'll do decoding, and it'll send the observable back, okay? Now, let's just kind of just go through this again using this picture. So you've seen this picture before if you've been here at 3:36 with my colleagues, Andrea and Aniket. It's a very general picture. The quantum control system is on the left-hand side. It's responsible for acting on the qubits. The QECi system here, obviously I'm going to show Riverlane's delta flow. The QECi system is on the left-hand side, and they're going to talk via this interface that was talked about before, the QECi, right? So what happens in quantum memory? Number one, the first thing that happens is the program. So the program will come down, and the control system is now running this program, right? First thing will happen. The control system will run the syndrome kind of extraction gates. So it's going to run them, control the qubits, get the measurement out. The measurement's going to be sent over this channel to the QEC system. The QEC system will do decoding. It'll take its time, right? And just as corresponding time it needs to take, and then it'll send the results back to the control system. Now, depending on the program and the control system, it might want the results back now, or it might want to wait for the results. If it's a real-time system doing something like a T-gate, it wants the results right now. If it's doing just normal things like quantum memory, it probably afford to wait, right? But in any case, at some point, the observable will come back, and the program that's running on the logical program that's running on the control system will want to do something with it. So this is kind of a general picture, right? So there's like in a scaled out system, which is doing fault tolerant quantum computing, you want this kind of handshake between the control system and the quantum error correction system, right? Both work kind of in lockstep with each other. Oops. Okay, so now let's talk about the second part of my talk about the extensions you want to make to your control system to let this happen, right? So I'm just going to walk through some features that kind of top of my head. I'm not going to go into too much detail. You can talk to me about them afterwards. So I've got 4 or 5 features here. So I think this is kind of nothing really, well, it's to do with fault tolerant computing in the sense that you want to control lots of qubits. So the first thing you want to do is to make sure that your control system is distributed, scaled out. And the sessions earlier, the talks earlier in the session have been about a lot of that, right? So I'm assuming that. And then let's start from the top. So we've got an open QASM program. So the most generic, kind of quantum programming language we have right now, every control system vendor has something specific, but they all kind of talk the same thing, right? So you've got your open QASM program, but it needs to have these QECi instructions embedded inside it, right? Inside it, because as soon as you do the measurement that's relevant to error correction, you want to send that measurement over. So that's a couple of additional commands that you want your program to have. So as soon as you have that, then you want your compiler. So this is now the compiler to do with the control system, right? So not our compiler, not any compiler, compiler to do with the control system. You want that to know how to translate it to some instructions that you'll have in your sequencer or your CPU or whatever control system you have, control kind of block you have. And we've seen some of these today in this session, whatever you have in your control system, right? So once you've got those, you want to come down and you want to know how your sequencer, how your CPU will execute those commands, right? So you need to modify additional extensions to your sequencer, to your CPU, to know how to execute those commands, right? And actually, there's a crude kind of example here, which is that you could see the QECi port as just a kind of an I/O port, right? And what all the sequencer has to do is to read and write packages to this I/O port, right? And the I/O port is obviously connected on this channel to the QEC system. The last addition I'm going to talk about is some readouts, some measurements are relevant to the QEC task, and others might not be, right? Because you might be doing some other work that's not to do with the QEC system, QEC thing that you're doing, right? Thank you. Yeah. So you need to know which of these measurements you want to route out through your sequencer onto the channel and into the QEC system, right? That's kind of to do with how you'll configure how these two systems work together. Okay, so I've got 2 slides left, 2 minutes left. So you notice that I had a whole list of co-authors. Probably half of them are Riverlane people, half of them are Inflection people. So everything that I've described so far, we've done this at the UK National Quantum Computing Centre Inflection testbed. So Inflection's added these features to their control system, and we've hooked up our QEC system with their control system, and we've run kind of very, very basic quantum memory experiments. On the left-hand side, it's so I'm sorry, kind of apologize for these pictures because these were the sanitized ones that were approved by both companies' legal and marketing departments. So on the left-hand side is Jan from Inflection with a Riverlane box. On the right-hand side is Okan from Riverlane itself. So they're a bit boring pictures, sorry. Okay, so last slide. I've only got one ask for you, especially for those people who have building their own control systems. Let's work together so that your control system can work with a QEC system, right? Ideally ours, and then you two can join this kind of hall of fame of people that we're working with right now. Thank you.
Questions? Actually, this is kind of combined with the talk earlier about the QECi because yes, we build the open source control system. We'd like to understand how this QECi is going to be open because I heard about the IP going to be included. And so is that going to be open? Is that going to be just a standard level or is to buy your IP to be able to implement in the QECi?
Yeah, so come and talk to us afterwards. So some IP we are giving out. So like the PHY layer of QECi, we're giving out to our partners. And we're giving a bunch of validation, verification IP as well, right? Source. And the standard we would like it to be as open as possible.